And then in the final study, we worked with the blade lean or stacking because it introduces a spanwise blade force. For example, in case of forward stacking, the shroud leads the hub in the direction of the rotation, and it increases the shroud pressure and reduces the hub pressure, and vice versa for backward stacking. And so clearly, this has an influence on the pressure jump across the shroud and is therefore an important design parameter to control cavitation. And in fact, we can specify this directly as part of the design process in TD1, as we can see here. So if you go to the stacking section, you just have to give the shroud a positive wrap angle, and this gives the blade a forward stacking when compared to the baseline, which has zero or radial stacking. As you can see in this 3D plot. And similarly, if you give the shroud a negative wrap angle, then this would give you a backward stacking. So in this way, two impeller configurations are generated, one with a forward stacking and another with a backward stacking condition near the trailing edge. And again, a close correlation can be seen between the TD1 and CFD plots, both confirming an increase in the shroud loading in the first case and an increase in the hub loading in the second case. Now, forward stacking increases the mass flow rate to the shroud, leading to a higher pressure jump here, and therefore a deepening of the pressure valley in this region, whereas backward stacking has the opposite effect, which means a reduction in the pressure valley and is therefore beneficial in terms of cavitation. And we can also see this in the CFD performance maps where the NPSHR has improved due to the backward stacking, but there is actually minimal impact of stacking on the pump head and efficiency. And also very interesting to see that the work distribution in CFD has remained unaffected by stacking. And this is because with inverse design, the computed blade angles will change to preserve the correct Euler head. And now with parametric study complete, we can proceed to a selection of the optimal design of these design parameters for maximizing peak cavitation performance while guaranteeing high efficiency levels together with mechanical constraints.